Ladies and gentlemen, one of the many pleasures of my job as director of the Isaac Newton Institute is to welcome the most distinguished mathematical scientists in the world to inform and to improve the quality of our lives by giving talks of various kinds. Most of the time these talks are of a scientific nature, but tonight it's a pleasure for me to welcome Barry Simon, who's going to give a talk. You all know who Barry Simon is, of course. I met him first in 1970. He won't remember any of this, but he was in Geneva, and I was a very young person, and he was visiting Bill Paris and other people. He was already a Winterkin, though he wasn't very much older than I am. Anyway, Barry Simon is going to tell us about the tales of our forefathers. So, history of mathematics. So it's a great pleasure to welcome Barry. He's going to speak for 90 minutes, so if you need a coffee break, keep that in mind. And there's an overflow room for people who arrive late. So Barry, please.
Thank you very much. It's a particular pleasure to give this talk here because in looking over the slides, I realized that there may be more mathematicians from Cambridge than from anywhere else. There certainly are more than from Oxford. This is not a mathematics talk, but it is a talk for mathematicians. It's dedicated to the notion that it would be good that our students realize that while Han Banach refers to two mathematicians, Mittag-Leffler refers to only one. While on the subject of names, I can't resist a semi-personal story. In the early 1980s, Mike Reed was visiting the Quran Institute, and at tea, Peter Lax took him over to a student who Lax knew was a big fan of the Reed-Simon books. This is Mike Reed, although not the 1980s. This is at his 65th birthday celebration not too long ago. This is Lax. Lax said to the student, "This is the Reed of Reed-Simon." Student, mouth falling open. "You're Reed? I thought Reed was Simon's first name." I digress, and not for the first time. 4 caveats before I begin the talk proper. First, I am not a historian, and I've no faith at all that what I'm telling you is true. None of the stories was made up, at least by me. Secondly, I regret that this is a tale about forefathers and not foremothers also, although 2 female mathematicians have cameos later. It's an unfortunate aspect of history that we used to ignore at least half of our mathematical talent. I'm glad we don't do quite so badly anymore. A third caveat is I'm an analyst. I learned many of these stories when working on notes for a series of analysis texts I'm writing, so I'll be focusing almost entirely on quote-unquote analysts. That said, prior to the 20th century, most mathematicians were more universal or less specialized, so analyst means actually most mathematicians if you go back a century. This is true not only for transcendent figures like Euler, who made it onto a Swiss franc note, Gauss. I once said this Deutschmark is no longer, because of the euro, it's no longer good currency, and somebody afterwards said, no, you can take it into any German bank and they'll honor it. And Riemann. So of course they're universal, they've made transcendent contributions. But for example, you might consider Camille Jordan, who lived did most of his work in the latter half of the 19th century. He makes significant contributions to algebra. We talk about Jordan normal form, Jordan Holder sequences, to geometry, the Jordan curve theorem, and to analysis, Jordan content and Jordan decomposition. This is not the Jordan of Jordan algebras and the Jordan von Neumann theorem. That's the physicist Pascal Jordan, best known as one of the authors of the Dreimann-Arbeit, the foundational paper of essentially so-called new quantum mechanics. The other two of the three authors are Heisenberg and Born. Born, by the way, in the world at large, is best known because he's Olivia Newton-John's grandfather. And some have speculated that this Jordan might have shared Born's Nobel Prize if it weren't for the fact that Jordan had very pro-Nazi views during the Hitler era and was in bad odor at the time in 1954. There's a last caveat. Mostly we remember mathematicians by applying their names to theorems and to mathematical objects. In this regard, I want to quote two principles which appeared in a lecture of Arnold. And he claims in the lecture, this is a printed lecture, that the principles are actually formulated and named by Michael Berry. The first is the Arnold principle. If a notion bears a personal name, then this name is not the name of its discoverer. And there's the Berry principle, which is that the Arnold principle is applicable to itself. Now, Berry's principle is certainly true. It's a very interesting exercise. If you type in Arnold's principle in Wikipedia, you get to a page that doesn't mention Arnold at all. You instead get to the page that says Stigler's law of epinomy, which Stigler stated in 1980 as no scientific discovery is named after its original discoverer. And Stigler says this principle is actually due to Merton. This is not the Nobel Prize winner in economics, but his father, who's a distinguished sociologist. And of course, Stigler remarked that since it was a discovery of Merton, it was appropriate to name it Stigler's law to validate the law. The first subject I want to discuss is mathematicians in their relation to families. One of the main points of this lecture is that we tend to think of mathematicians entirely in terms of, oh, this and that theorem, but in fact, mathematicians were people with the usual problems, triumphs, etc. And one way is to understand the connection with their roles as parents, children, wives, in-laws, and their impact on the mathematicians. Particularly interesting, of course, are cases where we have father-son, brothers, or most interesting in many ways is father-in-law, son-in-law. There's a famous joke in the yeshiva world where it tends the head of a yeshiva is often the son-in-law of the current yeshiva head. And the statement is, it's more often the son-in-law because after all, you get to choose your sons-in-law, you don't get to choose your sons. We start with the largest of the mathematical families. What's the largest of the mathematical families, anyone? Bernoulli. So the original family, and this is the most senior, Jacob, came from Belgium, but they fled. Oh, it fell off. Okay, sorry. They, for religious reasons involving the Catholic Protestant wars, they were they came from a religious Protestant family. They wound up in Switzerland. The most senior was Jacob Bernoulli. There was his younger brother, Johann, and Johann's son, Daniel, who was actually born in Holland because Johann was teaching there then. And there are a number of other cousins. There are several Nicholas Bernoullis that occur in the literature. Jacob was the most significant mathematically. He's the one who discovered the compound interest formula. He's the Bernoulli of Bernoulli trials, of the law of large numbers, and of Bernoulli numbers, the things that enter, for example, if you look at the formula for sums of inverse powers, the zeta function at even integers. Most of this work actually appeared posthumously in a book called The Art of Conjecture. Daniel's noted for Bernoulli's principle in hydrodynamics, and Johann for various contributions to differential equations, early work in the calculus of variations, and as we'll see, for L'Hopital's rule. To use modern parlance, the family was dysfunctional. Johann and Jacob were two in a family of 10. Jacob was Johann's senior by 12 years. There was tremendous jealousy between the two brothers. Jacob declared Johann was his student, and Johann objected to this. There was a huge priority fight over the solution of the isoperimetric problem, and a total break in 1697. Jacob was at that point convinced that Johann was after his chair in Basel, and indeed, when Jacob died a few years later, Johann got Jacob's chair. You may have noticed, it went by fast, I suspect you didn't, that there was 8 years between Jacob's death and the publication of this posthumous work, and this was due to squabbling between Johann and his nephew Nicholas. To me, the most shocking event involved books on hydrodynamics. In 1738, Daniel, that's the son of Johann, published a book on hydrodynamics that he'd largely finished writing in 1734. His father then published a book on the same subject using many of Daniel's ideas, but he predated the book, claimed that Daniel had taken the ideas from him. So the Marquis de L'Hopital was a French nobleman who was quite wealthy, and over a number of years he paid a large annual retainer to Johann Bernoulli, originally for lectures that Johann came and gave him on the new calculus of Leibniz and Newton. The Bernoullis were great proponents and really pushed through the applications of the calculus, and then after this for continuing mathematical advice. In 1696, L'Hopital published a book, The Analysis of the Infinitely Small for the Understanding of Curved Lines. It was the first textbook in differential calculus, and it was quite popular, and it contained what we now call L'Hopital's rule. He thanked various people in the preference, including Johann Bernoulli. But after his death, Bernoulli claimed the book was close to a verbatim copy of the notes of the lectures he gave L'Hopital, and in particular, he was responsible for L'Hopital's rule. Of course, Bernoulli wouldn't have said this before L'Hopital's death because he didn't want to lose this large annual retainer. Given the other priority disputes during the 19th century, historians of mathematics dismissed this claim, but in the 1920s, in the library in the University of Basel, the notes that a student had taken of Johann's lectures early of this were found, and they supported Johann's claim. There's no doubt that Johann Bernoulli's greatest contribution to mathematics concerns Euler. Both Euler's father and his mother's father were pastors, and they expected Leonard to go into the family business. During his studies, because pastors in those days, at least in the religion they were in, did get university education, Euler convinced Johann Bernoulli to give him private lectures, and fortunately, Johann had been a student with Euler's father in university, and he convinced Euler's father to allow Euler to go into mathematics rather than become a pastor. And he even helped Euler get his first job. Euler was a great physicist, was very prolific. It is estimated that about 1/3 of all research papers in mathematics and physics written in the 18th century were written by Euler. In 1775, when he was 68, he wrote over 50 papers. Let me emphasize, because someone misunderstood. I wasn't saying at age 68 he'd already written 50 papers. In that 1 year, he wrote 50 papers. The remarkable thing is that he'd been totally blind since 1766. He wrote these papers with the help of scribes and mathematical assistants. Among them were his son and grandson. This is the picture of the blind Euler. He's also was the author of textbooks on calculus, mechanics, some of them in use for 100 years, and he wrote the first great popular book on science, Lessons for a German Princess. His complete works run to 72 volumes, each in the 400 to 700 page range. While on the subject of fathers wanting sons to do something, I want to say something about Weierstrass. So Weierstrass was the son of a Prussian finance ministry bureaucrat who made a good living. It was actually, it was for someone who didn't have inherited wealth. Being a government bureaucrat in Prussia was pretty good, and he forced his son to study finance at the University of Bonn. Karl rebelled. The stories are he spent more time in the tavern than in the classroom when he was a student there, and he quit just short of a degree. There were negotiations. A friend of his father intervened, and there was a compromise reached that allowed Karl to go to Münster, get a degree there that would allow him to teach mathematics in gymnasium, in high school. By the way, this picture, which was outside my office in Mittag-Leffler, when someone said this was Weierstrass, I was rather surprised, because this is the young Weierstrass. This is the son of a Prussian ministry bureaucrat. How in the world did he have the wherewithal to have a picture painted of him? Turns out his brother is the one who painted this picture. He taught at gymnasium starting in 1841. During the 1840s, he had many, many unpublished works that established what we would now regard as the Weierstrass approach to complex analysis. Many of them were only published 50 years later when his complete works were published, and many of them he used as the basis for lectures to get ahead of the story that he gave at the University of Berlin. During the summer of 1853, he wrote a memoir in elliptic functions and sent it to Creel's journal, the Journal of Pure and Applied Mathematics, and it caused a sensation because the subject of elliptic functions had reached maturity 20 years before, and the fact that essentially an unknown school teacher that people had not heard of could produce important results in this subject, which was regarded as totally settled, he actually solved an open question, caused a sensation. Within a short time afterwards, it was arranged for him to be a university professor. A short time after that, he wound up at the University of Berlin, where he developed an active school in analysis. His lack of a degree was settled by arranging for him to get an honorary degree. One of my favorite quotes about Weierstrass comes from Corner's book in Fourier analysis, who's commenting on Fayet. So Fayet just enters. We're going to say more about him in a second. This is Fayet. Fayet's theorem on Cesaro summability of Fourier series, and Weierstrass's theorem on the density of the polynomials and the continuous functions. Fayet discovered his theorem at the age of 19. Weierstrass published his at the age of 70. With time, the reader may come to appreciate why so many mathematicians regard the second circumstance as even more romantic and heartwarming than the first. So since we've mentioned Feyer was born Leopold Weiss. He was born in Budapest, but there was a strong German tradition. His parents were, in fact, of the German-speaking part, and he was born Leopold Weiss. Weiss is German for white. I hope. And Feyer, and he was a student of Hermann Schwartz, which is German for black. In high school, he changed his name to Feyer, which is Hungarian for white, in part because he expected, and it was indeed true, that he had less anti-Semitism and it was easier for him to get a position in the University of Budapest. At least that's what I was told. One of his students was Fekete, which is Hungarian for black. His other students included Ries, M. Ries. F. Ries was a contemporary. M. Ries was one of his students. Polya, Zago, von Neumann, Turin, and Erdős. So Feyer, I believe one can claim, had the most impressive list of students, although we'll see another example of an impressive list of students in a few minutes. While on the subject of fathers and polynomial approximation, I want to mention that the father of Marshall Stone of Stone-Weierstrass was in fact the Chief Justice of the U.S. Supreme Court. Okay, the next subject I want to say something about is bastards. Here I mean literal bastards, not figurative bastards, but at the end of the talk, when I talk about the impact of Nazis and communists, we'll get to the figurative bastards. But now I'm talking about literal bastards. The parents of Stefan Banach were not only not married, but his mother essentially abandoned him 4 days after his birth, left behind nothing but the name Banach. He was raised initially by his father's parents and then by friends of his father's. And essentially as a teenager, he was left to fend for himself. He did study some mathematics, but he only managed to get a first degree in engineering. His life changed dramatically in 1916 when he was 24 because of Hugo Steinhaus. So Hugo Steinhaus was about 5 years older than Banach, but at this point he was already well established, and he had been appointed to be a professor in Lvov. But while waiting for that to start, he was living in Krakow and made a habit of strolling in the park in the evening, and he heard wafting through the air the words Lebesgue integral. He went and followed the voices to find Banach and his friend Otto Nikodym, and he was so impressed with the two of them, he took them with him to Lvov, and he always regarded Banach as his greatest mathematical discovery. Banach's dissertation defined what is now called Banach spaces. There were other discoveries, simultaneous discoveries, and with Steinhaus, he essentially founded a famous school of mathematics and the journal Studia Mathematica. This 200 zloty coin is worth a lot more, if you could get it, than 200 zlotys. It's actually a gold coin, and it's a memorial coin that was issued at the time of the International Congress in Warsaw. Steinhaus was a rather pleasant person from everything I've heard. I was told by Mark Kotz, seen here, that Steinhaus loved stories, and von Moe, of course, so did Mark Kotz, anyone who knows Mark Kotz. And a favorite story that Kotz passed on is the following he said he heard from Steinhaus. The acceptance of your work by the mathematical public will go through 3 phases. First, they say it's wrong. Then they say it's trivial. And finally, they say I did it first. And I once got a letter from someone in which, as you went through the letter, all three parts appeared. While on the subject of bastards, so Jean-Baptiste Leronde, pardon my French, d'Alembert, was found abandoned in the church of Saint John Le Rond. That's where Le Rond comes from. And he was named after John the Baptist, which is the church that he was named. So his name comes directly from that. He had been abandoned by his mother, whose literary salon was a social center during the reign of Louis XIV and XV. Her many lovers included Richelieu and Louis Camus Destouches, who was an army officer and was also d'Alembert's father. Neither parent acknowledged d'Alembert, but his father did arrange a foster home, and d'Alembert liked it so much that in fact he lived with this foster mother for 50 years, letting her take care of him, and was left an income by his unacknowledged father that allowed him to in fact pursue mathematics. He had also studied law, and until he got this stipend had studied what he intended to be a lawyer. He discovered the wave equation and found its general one-dimensional solution. He was an editor of the Encyclopédie Française, and that made him a member of the Académie Française. And one of his students was Laplace, and it is reputed he had a lot of trouble dealing with Laplace's fame when Laplace became probably the most famous scientist in Europe. Last of the on our list of bastards, again figuratively, is Andrei Kolmogorov. His mother died in childbirth and his father had nothing to do with him. He was raised by his mother's sister. Kolmogorov was actually his mother's maiden name. His father was a minor nobleman. He presumably, if there hadn't been the revolution, would have done okay, but in Soviet Russia, he was able to get an education, unlike Banach, who had problems. He was a wunderkind, just as Fayet made great contributions to Fourier's series at age 19. Kolmogorov was 19 when he found the first examples of L1 functions, whose Fourier series are almost everywhere divergent. A few years later, he found ones that were everywhere divergent. He went on to make numerous contributions to probability theory, to dynamics, to topology, to computer science. And his students include Arnold, Debruchin, Denkin, Gelfand, and Sinai. So he gives Fayet a run for his money, but the Hungarians beat out the Russians, I think. Kolmogorov was an important player in the Lausanne affair. So Kolmogorov's teacher was Nikolai Lausanne, and in turn Lausanne was a student of Egorov. Now, to most mathematicians, Egorov and Lausanne are just these two names that appear in their measure theory book. And they always have to stop. Which one is Lauzanne's theorem? Which one is Egorov's theorem? And that's all they know about them. Both, in fact, were victims of the 1930s Stalin reign of terror. Egorov, that's who's shown here, was quite religious and loudly objected to the way the Russian church was treated by the Soviet government. As a result, he was dismissed from his post in 1929. He was arrested in 1930, and he died in the middle of a hunger strike in 1931. So lest you think everyone lives a calm life, Lausanne was the center of a lively group. His students, it was called Lusitania. His students included also an impressive set: Alexandrov, Kinchin, Kolmogorov, Suslin, and Orazone. And he was a very powerful figure in the Russian Academy. In 1936, he was accused of anti-Soviet behavior and given what was essentially a show trial before a commission of the Academy. He was found guilty but received a... What?
Why do you say essentially?
Because it wasn't officially a trial. There was no judge and jury. Okay?
Show trial.
It was a show trial. So it was not, so I should have said a show essential trial. It was, he was found guilty, but received a mild sentence. Being found guilty in those days usually meant death. And the story is that for whatever reason, Stalin intervened personally to prevent his being executed, but he essentially lost all his power and influence, and it left him, in essence, a broken man. Among those testifying against Luzin were Alexandrov, Kinchin, and Kolmogorov. I think of this as essentially a mathematical patricide. 3 of his students testified against him, and it has the elements of Greek tragedy. There's widespread speculation about why Alexandrov and Kolmogorov testified against Luzin. By the way, one of his few defenders was Bernstein. These two were very close. They traveled together and shared a house. Whether they were having a homosexual relationship or only gave the appearance of one, there's a belief they were pressured by the KGB to testify against Luzin or be arrested for homosexual behavior. This is just a tragic situation. Good news! On January 17th, 2012, the Russian Academy formally rescinded their motion condemning Luzin. So the next, while I'm on the subject of bastards, again, certainly not. The production of a bastard, of course, involves 2 innocent people besides the child. In this regard, you should consider Sir John Littlewood.
He was not Sir, he was not knight. Just John Littlewood.
I thought he was. Okay, I'm certainly not going to argue with you about Littlewood. So consider not Sir John Littlewood. Just as one can't imagine discussing Stan Laurel without Oliver Hardy, one can't imagine John Littlewood without G.H. Hardy. This is actually a very nice picture, I think, of Littlewood, but this is, of course, a famous and lovely picture of Hardy. They are arguably the most celebrated and most successful mathematical collaboration ever. At one point, Harold Bohr, so this is Harold Bohr. Actually, when I first found this picture in Google Images, I thought they'd made a mistake because it looks a lot like Niels Bohr. But if you look closely, it's not. And in fact, they're brothers. Niels Bohr is his older brother. In their youth, Harold was much more known than Niels because Harold had been on their Olympic medal winning soccer team. And at one point, Harold Bohr said, "These days there are 3 great British mathematicians, Hardy, Littlewood, and Hardy Littlewood. Both were bachelor dons." When I don't give this at Cambridge, of course, they may have to. They had nice meals and rooms. They got to go to the high table. There was a bonus to staying single because if you married, you lost your right to rooms, and you could still go to the high table, although in those days I'm not sure what the rules were. Littlewood spent his entire career, except for a brief few years after his degree in Manchester, he spent his entire career in Cambridge. Hardy started, I say there, but I should say here, but he was very unhappy during the First World War. He was very friendly with Russell. Russell was dismissed for being a pacifist during the war, and there was a virulently anti-German...
He was not dismissed, he was not reappointed. not dismissed at all. His appointment came to an end.
Thank you. Hardy had many German friends, and there was a very anti-German attitude here. And so in 1919, he left for Oxford. He was very happy in Oxford, and in many ways would have preferred to stay there, but he returned to Cambridge in 1931, because in Cambridge, unlike Oxford in those days, one could keep one's rooms after retirement. And so that was the bonus that made him come back here. Despite being a bachelor in his later years, Littlewood traveled with his niece, Anne, who he eventually acknowledged was his daughter. I have a favorite, probably apocryphal story about Littlewood. Until his later years, when he was helped by medication, Littlewood suffered from severe depression, and so he didn't travel very much. On the other hand, Hardy was everywhere dense. Virtually all conferences in the 20s and teens, Hardy was there. He was well known everywhere on the continent and widely traveled. And there's a story involving a visit to England and the story has two different versions. And in some version, it's a visit by Edmund Landau, and in others, it's by Wiener, who upon meeting Littlewood exclaimed, "Oh, you exist? I thought Littlewood was a pseudonym Hardy used for his weaker papers." It's a widely reported story. I'm not going to say it's... And of course, Hardy pointed out that he regarded him, one of his signs of success is that he was able to work with Littlewood as somewhat close to being an equal. The next thing I want to discuss are fathers-in-law. Schwartz's father-in-law was Kummer, who you may have not heard of, but if you ever studied hypergeometric functions, you would have heard of Kummer. Unfortunately, students don't learn about hypergeometric functions anymore. Hermite was Picard's father-in-law, and in this regard, there's an interesting story. There's an interesting timeline. Picard got his degree. Actually, Hermite was not his advisor, but was one of his mentors. He then went off to Toulouse. In Toulouse, he proved his famous theorems, only then returned to Paris and was he allowed to marry Hermite's daughters. So I guess he had to prove himself or prove his theorems to be allowed. Schwartz was Paul Levy's son-in-law. Tate is Arten's son-in-law. He is a multi-generational. Courant was the father-in-law of Jürgen Moser, and more recently is actually posthumously Peter Lax's father-in-law. Peter's second wife is the younger sister of Moser's widow. In turn, Courant was the son-in-law of Runge, and Runge, well, it's not quite son-in-law, he married the niece of Paul Dubois Raymond. So this is many generations. Schwartz's great uncle was Hadamard. It appears he had no mathematical influence, just met him occasionally, but at some point he met the 16-year-old Schwartz and was absolutely just didn't understand how someone could not know about the Riemann zeta function at age 16. Pringsheim, who you may not have heard of, but it actually is, there are lots of nice proofs in complex analysis due to him. He was the father-in-law of Thomas Mann. Ehrlich was the father-in-law of Landau, who was in turn the father-in-law of Schoenberg. And Emile Borel, when he was 30, married the young daughter of Paul Appel. So he was the son-in-law of Paul Appel, who was... Besides mathematics, Borel was the French Minister of the Navy from 1925 to 1940. And even though in 1940 he was close to 70, he was active enough in the resistance during the Second World War that he received the Croix de Légion d'honneur for his resistance activities. Here's a story that is local that involves a non-mathematical father-in-law. So George Airy, whose functions you may have heard of, came from a poor background, managed to get through Cambridge by being a part-time manservant. In 1824, when he was 23, he met and fell in love with Richarda Smith, the daughter of the vicar of Chatsworth. In 1826, when he was only 25, he was appointed to the Lucasian Chair of Mathematics. Of course, I don't have to tell here, well, there are some people not from Cambridge. This is, of course, the most prestigious chair in science. Among its other holders are Newton, Dirac, and Hawking, or were. That's Airy, by the way. But Vicar Smith would not allow Airy to marry his daughter because the Lucasian chair only paid £100 a year. In 1830, the Plumian Chair of Astronomy, which paid £500, opened. Airy applied for it and resigned from the Lucasian chair and was able to marry Richarda, and he took his role as an astronomer seriously enough that he went on to become the Astronomer Royal. Another Cambridge story involves Grace Chisholm Young. Grace Chisholm studied mathematics in Cambridge with William Young, who was her tutor. She then went to Goddington and got a degree in 1895, supervised by Felix Klein. She returned to England, married her tutor Young, and she encouraged Young to become active in research. He had not been active in research. Works credited to him once he became active again is the independent rediscovery of Lebesgue integration, but he's the Young of the Hausdorff-Young inequality, of Young's convolution inequality, and of Young's inequality on conjugate harmonic functions. He's not the Young of Young tableau. That's Alfred Young, who was a clergyman and amateur mathematician. It's clear that some of Young's work was joint with his wife, but it's not clear exactly which papers. There is, however, an interesting letter he wrote his wife at one point. The fact is, our papers ought to be published under our joint names. But if this were done, neither of us would get the benefit of it. No, mine the laurels now and the knowledge, yours the knowledge only. Everything under my name now, and later when the loaves and fishes are no more procurable in that way, sorry for the flowery language, everything or much under your name. At present, you cannot undertake a public career. You have your children. Not mathematics' greatest hour. It was typical of the time, but it's still not, well, not Young's greatest. Okay. So I want to next say something about Weil and Schrödinger. So Erwin Schrödinger and Hermann Weil were both professors in Zurich in the 1920s, coupled scientifically and due to their work on quantum mechanics. Shortly after Schrödinger's work, Weil wrote his famous book on group theory and quantum mechanics. Since I found these three, and it's relevant to the story, I found these three different pictures of Hermann Weil. This dreamy young man is about 1912. This is the Weil of Weil's law, the one on asymptotics of eigenvalue counting. This dapper middle-aged man is the Weil of the mid-20s. This, if you will, is the Weil of group representations in the Weil group. And this is Weil in about 1950. If you know about the Schur-Lelesco-Weil inequality, that's a theorem he proved then. But they were not linked only scientifically. As one biographer of Schrödinger put it, those familiar with the serious and portly figure of Weil at Princeton, think of the last picture, would hardly have recognized the slim, handsome young man of the 20s with his romantic black mustache. His wife, Helene Joseph, from a Jewish background, was a philosopher and literature. Her friends called her Heller, and a certain daring and insouciance made her the unquestioned leader of the social set comprising the scientists and their wives. Annie, Schrodinger's wife, was almost an exact opposite of the stylish and intellectual Hella, but perhaps for that reason Weil found her interesting, and before long she was madly in love with him. The special circle in which they lived in Zurich enjoyed the sexual revolution, if enjoyed is the right word, a generation before the United States. Extramarital affairs were not only condoned, they were expected, and they seemed to occasion little anxiety. Annie would find in Hermann Weil a lover to whom she was devoted body and soul. So when you hear about Weil and Schrödinger, you should not only think of the mathematical connection. We close our stories of families with a love story. Alexander Lyapunov is known for his work on stability of ODEs, in particular the Lyapunov exponents, which many of us have heard a lot about in the last week, and on his work on the central limit theorem. In 1886, he married Natalia Sechenov. He'd actually studied with her father as a teenager. His father was his second or third cousin. Lyapunov was a student of Chebyshev in St. Petersburg. He took a position in Kharkov in 1884, and when Chebyshev died about 1900, Lyapunov was given Chebyshev's chair. In 1917, Lyapunov took a position in Odessa since the doctors thought the climate there was better for Natalia's tuberculosis. Her condition worsened and she passed away in 1918. Later that same day, the distraught Lyapunov shot himself in the head and died 3 days later. I want to say a little bit about educational. Even with 90 minutes, I'm going to have to do this one a little bit fast because there's still a lot of interesting stuff to talk about. I'll mention Dirichlet very quickly. Actually, all I'll say about him is that Dirichlet's wife was in fact Felix Mendelssohn's sister, and the Dirichlet's, Mendelssohn's, and Jacobi essentially every Sunday got together, played music, games, and other things, so they had a close social connection. Bernstein was a Jewish-Ukrainian mathematician known for his work in approximation theory, for integral representations for completely positive functions, and I know some of his fans will claim he's, of course, I didn't say enough about his mathematics. He went to study in Paris, spent 3 years then in Göttingen with Hilbert, and submitted a thesis in Paris, which he defended in 1904 before a committee of Poincaré, Hadamard, and Picard, certainly distinguished PhD committee. The thesis solved, in fact, or partially solved, Hilbert's 19th problem. It was one of the first of Hilbert's problems to be solved. Despite having gotten a PhD in Paris with this committee, having solved one of Hilbert's problems, when he returned to Russia, he had to become a graduate student because his degree was not recognized. He had to submit a master's thesis and later submitted a PhD thesis that went a ways towards solving Hilbert's 20th problem. While on the subject of education, so this is a picture that's actually on the wall in the Danish Academy of Sciences. And it happens about 2.5 years ago. I attended a conference there. There was this huge painting, and the president of the Danish Academy, when he was welcoming us, the room we were in had this painting, and he went and pointed out this painting was about 1905. He pointed out various people in the picture. And I asked him where was Jensen, because Jensen I regard, now the Danes may not, as the greatest Danish mathematician, you could argue perhaps one or two others. He's, of course, revolutionized the study of convex functions, and he invented something called Jensen's formula, which is used in Neven linear theory and in complex analysis. I was informed he'd spent his career as an engineer for the telephone company. I knew that. Didn't have an advanced degree, and so therefore could not be elected to the academy. If one wants to talk about degrees and interesting lives, Misha Kotler, he's known for something called Kotler's lemma, sometimes Kotler-Stein or Kotler-Knapp-Stein. It's a wonderful result that's critical for estimating integral and pseudo-differential operators. This afternoon we heard about Calderon-Valancourt. That actually uses, most of the proofs use some version or other of this lemma. And he had invented actually to handle L2 bounds on higher dimensional Hilbert transforms. That paper is a wonderful paper. Here's what Charlie Pfefferman said about his interaction with Kotler. This is when Pfefferman was a postdoc. Actually, it was a year that Pfefferman started as a postdoc and ended as a full professor. And at the time, Kotler was almost 60. Kotler was one of the kindest and most self-effacing people I ever met. One of my secret ambitions during the few months we were together in Chicago long ago was to succeed in walking through a doorway after Misha rather than let him hold the door open for me. In this, I failed. When Kotler was born in the Ukraine in 1912, his father was the manager of a local mill. That made him a thoroughly bourgeoisie, representative of the bourgeoisie. So after the revolution, he was regarded as a pariah, and as punishment, his children were not allowed to attend school. Probably didn't help that he was Jewish also. So Misha had exactly 1 year of formal schooling. But his father taught him some mathematics and also to play the piano. In 1928, the family was able to emigrate to Montevideo, Uruguay. The four of them, his mother, his father, his brother, and he lived in a single room. His father sold newspapers on a downtown street corner. His older brother became a tramway conductor, and Misha played the piano from 4 p.m. to 4 a.m. in a rough harbor bar. That's probably a polite name. It was probably a lot more than just a bar. Not long after arriving, the senior Kotler came in first in a national chess tournament in Uruguay, and the fact that a member of the lower classes did this caused a considerable stir in some news coverage. The articles mentioned the winner claimed to have a mathematically gifted son. This was noticed by Rafael LaGuardia, who was a professor of mathematics in Montevideo and had been a student of Picard. He sought out Misha, invited Misha to attend his seminar, and even allowed Misha to teach his graduate students a course in number theory. He also helped Misha upgrade his job to playing in a chamber music trio in the fanciest hotel at a resort near Montevideo. In 1934, Ray Pasteur, who had been a student of Felix Klein and was spending half his year in Madrid and half in Buenos Aires, visited Montevideo. Now, while LaGuardia had a good background, there was not serious mathematics being done in Montevideo, but Ray Pasteur was definitely connected to deep analysis, and he gave some lectures that caught Kotler's fancy. So Kotler was drawn to Buenos Aires, where he learned more mathematics, shifted from earning his living as a pianist to being a tutor of mathematics. He got a job at a university research institute, but was fired after 6 months when the authorities learned he had no degree. So he continued to tutor. He corresponded with Fréchet, published his first paper, and he met a student of Ray Pasteur, who was his wife They actually were married for 70 years until Misha passed away. So it's a fairly long, successful marriage. From the mid-40s onwards, several American foundations sponsored trips by U.S. mathematicians to Argentina. Among them were Adrian Albert, George Birkhoff, Marshall Stone, and Zygmunt. It was during one of these trips that Zygmunt discovered Calderon, an engineer, and brought him to Chicago with money from the Rockefeller Foundation. And Stone in Chicago convinced them that Calderon should get a degree, and shortly afterwards he was on the faculty. There's actually a great story about some initial interactions between Zygmunt and Calderon. So Calderon had read Zygmunt's book and thought it was wonderful, and one day they were talking and Zygmunt said, you know, the following problem has always seemed to me very difficult and I haven't been able to make any progress on it. Calderon looked at him and said, I don't understand. You can get that from the method in one of the proofs in your book. So Zygmunt said, I don't believe that. And so Calderon took out the book, showed him the theorem. He said, it's the proof of this theorem. They looked at the proof, and the method wasn't. It turned out Calderon had read the theorem but found his own proof, and it was his own proof that solved Zygmunt's theorem. Somewhat earlier than Zygmunt discovering Calderon, Birkhoff had met Kotler and was so impressed that he recommended Misha for a graduate Guggenheim Fellowship, which would allow him to come to the United States and get a PhD. And the Guggenheim Foundation awarded him this fellowship. Alas, Birkhoff died shortly after he received the letter from the Guggenheim Foundation, and before he'd let Kotler know that he'd been awarded this fellowship. But the letter was found among his papers by his son, Garrett Birkhoff, also a noted mathematician. And even though the award was made in 1944 and was only, it was in 1950 that Kotler made it to Yale, the Guggenheim Foundation was willing to honor. In those days, you know, when Garrett, of course they would have honored it. I mean, the bureaucracy was much less. And he worked on and completed a PhD thesis on ergodic theory with Kakutani. But when the Yale administration learned he had no prior degrees, they refused to award Kotler a PhD. Marshall Stone then stepped in. Marshall Stone was by then the chair in Chicago, and he suggested that Misha come to Chicago, where he said, things are much more flexible, and I guarantee you can get a degree here. Kotler insisted on doing a new thesis, which he wrote on harmonic analysis under Calderon. He then went back to Buenos Aires, where he proved Kotler's lemma, spent much of his career as a professor in Buenos Aires. He's known for, among the undergraduates who he later sent to the US, are two fairly well-known mathematicians. Unfortunately, after the takeover by the military junta, Kotler went into exile. He did eventually return to Buenos Aires, but he had a rather eventful life. I'm not going to say a lot about high school teachers except to mention a few. Turns out, maybe it's true, in some places it's true again, it was often difficult to get a higher degree. You would get a PhD, and to get a job at an institution of higher learning was often difficult, and so many mathematicians had their first job teaching high school, and some of them did their best work while they were teaching high school in the evenings. Among them was Kuma, who actually had Kronecker as one of his students in class, Hadamard, who had Frechet as one of his students in high school, and later was his thesis advisor, but Hadamard proved the prime number theorem when he was a high school teacher. Lebesgue invented his measure when he was teaching in high school, and Bayer invented monotone classes of functions while he was a high school teacher, and Nevin Linna developed value distribution theory while teaching high school. They're not, I think, on the list, but Volterra and Montel were other examples of people who did some of their best work while high school teachers. So I want to say a few more words about Nevin Linna. He made a big splash with this work in 1925 and was shortly afterwards made a professor at the University of Helsinki. He actually became rector in 1941. He cooperated with the Nazis and was chair of the support committee for the Finnish branch of the Waffen-SS. After the war, he was dismissed as rector and spent some amount of time in Zurich, partly because he was not being treated very well in Finland because of his activities during the war. His defenders claim he was not so much pro-German as anti-Russian. He fought actually in the Finnish-Russian War at the time of the Russian Revolution and supported Finland in its 1939 war with Russia. He was later rehabilitated enough to be president of the ICM, but I am among those who question the appropriateness of naming an ICM prize after the head of the support committee for the Waffen-SS, but that may just be me. Some mathematicians are either underappreciated in their lifetimes or even sometimes now, and I'm going to talk about a few of them. Fourier was more an engineer and physicist than a mathematician. Because of his practical abilities, he had high political appointments. He went to Egypt with Napoleon and ended up the governor of Lower Egypt. He spent many years as prefect, which is essentially the governor of the province that includes Grenoble under Napoleon when Napoleon was emperor, and he's responsible, he didn't by hand, but he was responsible for the construction of the Turin-Grenoble highway. So, and he wound up actually as a baron. He is, of course, best known to us for his book on heat flow, which includes both Fourier series and Fourier transforms. Good enough to get him on a coffee cup. He submitted it to the French Academy in 1807. A committee of Lagrange, Laplace, Monge, and Lacroix, not minor mathematicians, questioned his notion of expanding any function in Fourier series, and it was only in 1822 that this book that he submitted in 1807 was published. So the next time the annal sits on one of your papers for 5 years, just think it was 15 years for Fourier. In 1829, Fourier's student Dirichlet actually proved that almost any function, he proved that C1 functions, piecewise C1 functions, in fact had convergent Fourier series. That's why he invented the Dirichlet kernel. So Fourier was even right. Fourier also studied Egyptian history while he was there. And here's what Corner, who I quoted earlier, says in his book on Fourier analysis. It's a great quote about Fourier's work on Egyptian history. Apart from his prefectorial duties, Fourier helped organize the description of Egypt. Fourier's main contribution was the general introduction, a survey of Egyptian history up to modern times. An Egyptologist with whom I discussed this subject described the introduction as a masterpiece and a turning point in the subject. He was surprised to hear that Fourier also had a reputation as a mathematician. One tends to think that theorems are either true or not and can't be controversial, but radical new approaches can face strong attacks. I'll consider briefly for some of them, but I want to begin with the three now central pillars of modern mathematics. The first is Georg Cantor. This is, of course, the Devil's Staircase. I couldn't resist putting this picture, which I commissioned for my book, of the devil dancing up the Cantor function, the Devil's Staircase. His work on counting infinities, especially his proof of the existence of transcendentals, and that r and r squared had the same number of points, things that we would now, that is almost taught in high school to bright high school students, caused great discomfort. Kronecker was an implacable foe, and he blocked Cantor's dream of a professorship in Berlin. Poincaré thought that Cantor's work was a disease that he hoped would be cured. Cantor was born in St. Petersburg, spent most of his life in Germany, and has been described variously as Russian, German, Danish, and Jewish. His paternal grandparents indeed were Danish Jews, but they were unobservant enough that his grandfather gave all his children names of Christian saints. Cantor's father was a Lutheran, and his mother was raised as a Russian Roman Catholic. Nevertheless, Cantor suffered from anti-Jewish prejudice during parts of his career because, given his name, it was natural to assume that he was Jewish. His initial burst of activity started in 1873, ended about 1885 with his discovery of the Cantor function. There were second few years a little later. In between and in the later years of his life, Cantor was incapacitated by depression, so much so he institutionalized himself for parts of these periods, and he's now believed to have suffered from bipolar disorder. I'm not going to say a lot about Lebesgue and Schwartz. I'll say a little, but there's this great quote from Strickhartz that I want to at least begin with. Distribution theory is one of the two great revolutions in mathematical analysis in the 20th century. It can be thought of as the completion of differential calculus, distribution theory is one of the two great. Can be thought of as the completion of differential calculus, just as the other great revolution, measure theory, can be thought of as the completion of integral calculus. There are many parallels between the two revolutions. Both were created by young, highly individualistic mathematicians, namely Lebesgue and Schwartz. Both were rapidly assimilated by the mathematical community and opened up new worlds of mathematical development. Both forced a complete rethinking of all of mathematical analysis that had come before, basically altered the nature of the questions the analysts asked. But the assimilation, while rapid in that it was a short period, wasn't overnight. Hermite initially dismissed Lebesgue's work as insignificant, and as for Schwartz in his obituary, Trev, who was a student of Schwartz, tells the following story. In 1948, Lawrence Schwartz visited Sweden to present his distribution to the local mathematicians. He had the opportunity of conversing with Marcel Rees. Having written on the blackboard the integration by parts formula to explain the idea of a weak derivative, he was interrupted by Rees saying, "I hope you have found something else in your life." Later, Schwartz told Rees of his hopes that the following theorem would eventually be proven. Every linear partial differential equation with constant coefficients has a fundamental solution. The idea of fundamental solution was only made precise by distribution theory. "Madness," exclaimed Rees, "this is a project for the 21st century." Of course, the theorem was proven 3 years later by Ehrenpreis and Malgrange. But Schwartz had some amount of... Part of the irony, of course, is that it was two of Rees's students, namely Gording and Hormander, that used distribution theory to reformulate and study quantum field theory and PDEs, respectively. By the way, this is another parallel. While Lebesgue invented Lebesgue measure, it was Fatou and F. Rees, more than anything else, that put Lebesgue measure on the map, and similarly, more than anything else, it was Hormander that made distribution theory as widely accepted as it was. I have time for Helly. I usually have to skip Helly. Edward Helly is underappreciated and is a paradigm for may you live in interesting times being a curse. I used to say it was a Chinese curse, but after one of these talks, a young Chinese student came up to me and said, no, it's not a Chinese curse, so I've made it a curse. In 1912, while Helly was teaching high school, he wrote a brilliant paper about continuous functions on 0, 1. For this space, he proved the Hahn-Banach theorem. Hahn-Banach did their work 10 years later, and the argument he gave is the induction step is essentially the one you find in all the books. That's first appeared in his paper, and the argument that he gave, because he used ordinary induction, worked for general Banach spaces, which had not yet been defined. He also, in the same paper, proved sequential weak compactness of the unit ball, a result that's sometimes called the Helly selection theorem. The work of Alaglu, we call this now the Banach-Alaglu theorem, was 25 years later. So why isn't Helly better known? Well, when the war broke out in 1914, he enlisted, serving as a lieutenant. In 1915, he was shot in the lung and captured by the Russians. He spent the next few years in a hospital and then in a prison in Siberia. He suffered from the lung injury and strain on his heart for the rest of his life. Even after the Russian involvement in the World War ended, he was not repatriated because during the Civil War, travel across Russia was difficult. He only returned to Vienna in 1920. He wrote another paper. He was able to get a habilitation, but could not get a paid position. His wife believes that because he was Jewish, and because Hahn, who was controlling the positions and was himself Jewish, wanted someone younger. This, by the way, is the same Hahn of Hahn-Banach. However, it's not clear that Hahn knew of Helly's earlier work on this subject. Banach probably knew something about the paper. Helly then found a position in a bank, but the bank failed in the crash in 1929. As I said, living in interesting times can be a curse. He eventually found work as an actuary. In 1938, he and his wife decided to flee Austria when the Germans invaded, and Einstein, who knew of his work, actually helped him obtain first a teaching position, and finally he was offered a professorship at Illinois Institute of Technology, but died of a heart attack shortly thereafter. To me, Helly is one of the heroes of early analysis, and it's I think I don't have time for Fréchet. The slides, by the way, are supposed to originally be soon be posted here, and you can also find them if you go to my website, sort of at the bottom of the list of papers, I think. But I'm going to skip Fréchet. Okay. We end with death. Right? What else can you? So it isn't such a downer. I want to begin by noting that many mathematicians have lived to ripe old ages, 70s, 80s, 90s, and even over 100. Indeed, as Odletsku is quoted as saying, so there is a very famous right-wing political commentator named Derbyshire, who actually wrote a book called Prime Obsession about the Riemann hypothesis. It's actually got alternate chapters on mathematics and history. The history is very readable and lots of fun to read, and the mathematics is not quite sterling, but it's not awful. Right? Who knows why he spends his time as a right-wing commentator. In any event, he quotes Odletsku as saying the following: It has been said that whoever proved the prime number theorem would attain immortality. Sure enough, both Hadamard and de Villers-Poussin, who independently proved the theorem, lived into their late 90s. It may be there's a corollary here. It may be the Riemann hypothesis is false, but should anyone manage to prove its falsehood, to find a zero off the critical line, he will be struck dead on the spot and his result will never become known. Indeed, Hadamard lived to age 97, but in fact, in both the First and Second World Wars, he had sons killed. De Villers-Poussin, who was Belgian and was made a baron by the Belgian king for his work in number theory, lived to be 95. And Erdős and Selberg, who found the first quote-unquote elementary proof of the prime number theorem, lived to ages 83 and 90 respectively. So some mathematicians live to a ripe old age. Gelfand and Henri Cartan both lived into their hundreds. And the irony of the quote is that Olitzko has done computer searches to try to find zeros off the critical line. As we know from Schramm's death, accidental death is still with us. The strangest accidental death that I know of a mathematician is Jürgen Graham. So he was not a young man when this happened. He was 66. Yes, 66. He is Jürgen Graham. This is the Graham of Graham-Schmidt. He was walking to a meeting of the Danish Academy. He was struck by a bicycle and killed. I think of Graham while watching bicycles whizzing by in Copenhagen. If you've ever walked on some of the streets in Copenhagen, there were these bicycle paths, and boy, do they whiz by fast. And I think of Graham when I see them. Urzon, who you know of probably most of all for his lemma, he actually proved that any second countable normal topological space is metrizable, and during the proof of that theorem, he used what has been called Urzon's lemma. In 1924, he and his friend Alexandrov traveled from Russia, from the Soviet Union, to Göttingen in Paris, and went on to vacation in Brest on the south of France, in the coast of France, sorry, the west coast, not the south. While swimming, he was swept off by a wave and he perished at age 26. Raymond Paley did remarkable research in harmonic analysis with Littlewood and Polya and Zygmunt in Cambridge. He was a student in Cambridge. He then went to the US where he did work with Wiener. And you know, there's the Littlewood Paley work, and there's some important Paley-Zygmunt work on random analytic functions, and there's of course the famous Paley-Wiener theorem. While in Cambridge, Mass, he went on a skiing vacation in Banff, where he was killed in an avalanche also at age 26. Modern medicine can best be appreciated by thinking about deaths in the 19th and early 20th centuries that would likely have been avoided with current technology. Among those to think about are Abel, Eisenstein, and Riemann. They died of lung ailments at ages 26, 29, and 39 respectively. They both had tuberculosis. Riemann, I think it was complications of pleurisy. I learned that by reading a book by real historians. You often hear it said that he also died of consumption, but I don't think that's the case. Stilches died at age 38. I have not been able to find out the cause. And Minkowski died at age 44 of a burst appendix. Of course, some burst appendices can kill you these days, but usually not. And he certainly, and in this regard, well, I do have time. So before I talk about anyone, I should mention Riemann. So people, of course, know Riemann's name because everything he did, but what many people don't realize is unlike Euler, who has these, this huge number of papers. Riemann's total output was about a dozen papers. Several of them were posthumous. And in particular, there are 6 monumental masterpieces, and each of them has a remarkable amount of stuff. So it's one paper. In fact, his thesis, I think it's in fact, I know it was one of his thesis papers, he defined the Riemann integral, but he did that because he wanted to study Riemann series, and the paper goes on to prove what we now call the Riemann-Lebesgue theorem and Riemann local convergence theorem. Another is his basic complex analysis. One paper, Cauchy-Riemann equation, removable singularities, Riemann mapping theorem, the notion of Riemann surface. That's all in a single paper. Single paper has all of Riemannian geometry. He began by defining a metric, defined geodesics, and defined Riemann curvature, all in one paper. There's the relatively short paper on the Riemann hypothesis. I'm not going to, okay. It's worth quoting Hilbert's tribute of Minkowski because it's so charming. Hilbert and Minkowski were very good friends. They were students together where they were both very much influenced by, I'm blanking on the name, theorem on the, never mind, I'll remember it later. Hilbert actually encouraged Minkowski to apply for a position in Göttingen, and they were colleagues for about 10 years. Hilbert spent about a year full-time in drawing together Minkowski's unpublished work on convex functions after Minkowski's death. Since my student years, Minkowski was my best, most dependable friend who supported me with all the depth and loyalty that was so characteristic of him. Our science, which we loved above all else, brought us together. It seemed to us a garden full of flowers. In it, we enjoyed looking for hidden pathways and discovered many a new perspective that appealed to our sense of beauty. When one of us showed it to the other, we marveled over it together, and our joy was complete. He was for me a rare gift from heaven, and I must be grateful to have possessed that gift for so long. Now death has suddenly torn him from our midst. What death cannot take away is his noble image in our heart and the knowledge that his spirit continues to be active in us. Finally, I turn to the promised discussion of figurative rather than literal bastards. I want to talk about the depressing view of what Hitler and Stalin and their systems did to various mathematicians. I'm not going to try to give you these long lists. I could. I'm instead going to focus, with regard to the Nazis, on 2 victims of the Nazi mayhem, namely Felix Hausdorff and Isaiah Schur. Hausdorff was an urbane Jew, had more of a name in literature and philosophy, where he wrote under the name Mongré, than in mathematics. In fact, in the 1930s, early 1930s, there was a book published on Jewish contributions to German culture. Mongré was listed among great German Jewish philosophers. Hausdorff was not listed among the mathematicians. This was especially true before he moved from Leipzig to Bonn in 1910. In Bonn, study is the last name of a student of Karateadori, got him interested in geometry, and within a few years, Hausdorff had axiomatized topology, found the precursor to the Banach-Tarski paradox, and had invented the Hausdorff metric, Hausdorff measure, and Hausdorff dimension. As the 30s progressed, things got progressively worse. He was dismissed from his position in 1935, In January 1942, expecting to be picked up for deportation to the camps in the East, Hausdorff, his wife, and her sister took overdoses of barbiturates and died. Schur was a Jewish mathematician, for many years a professor in Berlin. His contributions are well known. In the early 1930s, he turned down several invitations to leave Germany, thinking that this was Germany after all, and they would come to their senses. I've also heard that he was by then, 1930, he was then 25, he was then over 60 and knew the invitations were from England and the US, and he did not know English very well and was worried about having to teach in a non-native language. In 33, he was dismissed from his position. In 38, he was pressured to resign from the academy. Bieberbach remarked, "I find it surprising that Jews are still members of academic commissions." I promised a mention of the bastards. Bieberbach, Teichmuller, and Blaschke certainly qualify for that title. I may tell the story, I'll tell you anyway. So Zago, in the 50s, after he was in Stanford, used to give complex analysis classes and talk about products. And Zago has a reputation of being one of the gentlest, sweetest men you will ever meet. And a student came up to him and said, "Professor Zago, I don't understand. Everyone else calls them Blaschke products, and you call them products." And he said, "I will not say that man's name." The following story is told by Schiffer to illustrate the isolation and humiliation suffered by someone like Schur. Schur told me the only person at the Mathematical Institute in Berlin who was kind to him was Grunsky, then a young lecturer. Long after the war, I talked to Grunsky about that remark, and he literally started to cry. You know what I did? I sent him a postcard to congratulate him on his 60th birthday. I admired him so much and was very respectful in that card. How lonely he must have been to remember such a small thing. In 1939, Schur was allowed to leave Germany for Palestine, but the exit tax took all his savings. He was unable to find a position in a country that had many other mathematical refugees. Toeplitz was also unable to find position, and it had at the time a single academic institution, which was not very large, the Hebrew University, who already had 2 permanent math faculty. Schur was destitute, poor, and spiritually broken, and died in 1941. Finally, I want to say something about Fritz Noether, so I can show the Soviet side, who was the brother of Emmy Noether. Emmy is more celebrated than Fritz, but Fritz made one great discovery. In 1921, he realized that certain singular integral equations were non-compact, but had an integral invariant, which we now call their index. 30 years later, in others' hands, this blossomed to the theory of Fredholm operators, which was made for the Atiyah-Singer index theorem and the related work of Gelfand. While they're called Fredholm operators, they really have almost nothing to do with Fredholm. Fredholm only discussed compact operators. Both Emmy and Fritz had German positions from which, as Jews, they were dismissed in 1934. Emmy went to the US and died of cancer. The story's a little more complicated a year later. Fritz went to Tomsk, which is somewhere in the Soviet Union. In 1937, he was accused of being a German spy and imprisoned. In 1941, he was shot for anti-Soviet propaganda. Good news, in 1988, the Supreme Court of the Soviet Union officially exonerated Fritz. This is a wonderful picture that I had to include of Emmy. That's the family. His father, Max, was a noted physicist. That's Fritz. I hope you've learned that our forefathers are fascinating and that you'll consider using Mr. Google and Miss Wikipedia to look up the names you find on theorems. And now a word from our sponsor. So I have 5-volume set of books which I'm expecting the AMS to publish in about sometime in the fall, called A Comprehensive Course in Analysis. If you want more information, if you Google Simon Comprehensive Course Preview, you'll go to a page off my webpage that has tables of contents and more on the subject matter. There's real analysis, basic complex analysis, advanced complex analysis, harmonic analysis, and operator theory. Thank you. Of course, I'll take questions.
We've time for a few questions. There's wine waiting outside, so you mustn't. So, any questions?
Yeah.
Which of these many mathematicians did you feel personally closest?
That's a very hard question to answer. The one I probably respect the most is Riemann, but I can't claim to be close to him. I don't know. I haven't thought about it, and there are too many names there. You know, one of my unnamed who didn't appear here, underappreciated during his lifetime, didn't appear on the list of them, is Loevner. I mean, Loevner was a great mathematician, but both of he has two great contributions, and sort of, it's quite clear when in his 60s, it was arranged for him to talk to the AMS, and he talked about these two works, and you could sort of read between the lines that somehow he didn't feel they were very much appreciated. And of course now, certainly Loevner evolution is talked about all the time, and the matrix monotone theorem, it's you know, probably my next book will be on Loevner's theorem on matrix monotone functions, because it's such a wonderful theorem, and you know, any important result in analysis is the basis for a proof of Loevner's theorem. So, but I can't really answer that. There are, by the way, the book. So I wrote it was in writing the books that I learned most of these stories. So you'll find even more stories in the notes of the book.
Anything else? Okay, on that note, before I ask you to thank once again Barry Simon for this wonderful, amusing lecture, when you leave the room, please take your belongings with you, because the staff will want to lock it up while you're drinking your wine, and it may not be possible to recover stuff that you leave here after the wine reception is open. On that note, let's go and have a glass of wine. But first of all, thank Barry for a wonderful lecture.